All right, so we got two more questions from the AP Physics 1 2024 free response questions, our experimental design and our qualitative quantitative translation. So questions 2 and 3 from the 2024 AP exam. All right, question 2, you have a spring with unknown spring constant and you're asked to determine the spring constant. You have cylinders of unknown mass, a stopwatch, and a digital scale. And you're asked to list quantities that you would measure and describe the overall procedure. All right, this is not bad at all, actually. This is a pretty simple one. So things that we need to measure, right, stopwatch and scale, are a couple of things. Now, you could do this in a couple of different ways, but I'm going to measure the masses of the cylinders. And let's call that M. And then let's also measure the period of oscillation. How do I know that? Well, if you take a look, you're given a stopwatch and scale, you're asked to find spring constant on your equation sheets. There's only one equation connecting all three of those together. It's the period of oscillation is equal to 2 pi square root of M over K. So as we're writing our procedure, let's go ahead and refer to that. So the first thing that you're going to want to do is weigh the different masses using the digital scale. All right, weigh each different mass, each different cylinder using the digital scale. What we can do for step 2 then is hang one cylinder from the end of the spring and release the spring. Actually, before we do that, and release the spring from rest. Let's actually make that step 3. Step 3, start the stopwatch as you release the spring from rest. All right, and then step 4 is stop the stopwatch after counting the time for 10 full cycles. Again, you could minimize experimental uncertainty in a few different ways. This is my way of doing it, where you actually count the amount of time that it takes for 10 full cycles and then divide the total recorded time by 10 to obtain the period of oscillation. All right. And then what you could do is you could repeat steps 2 through 5 once more for the cylinder. Then replace the cylinder with a different cylinder and repeat steps 2 through 6. There you go. So what you have now is you have an experimental procedure that'll actually allow you to measure both mass and period. Steps 5 and 6 are designed to help us reduce experimental uncertainty, and then step 7 allows you to actually use different cylinders. All right, so what would you plot to actually, and by the way, I would say that the table is probably going to be 1 point. Your experimental procedure, let's see, probably 4 points, maybe. I'm not really too good with determining that. I would say maybe 2 to 3, actually. So let's say a total of 3 to 4 points for part A. All right, so moving on to part B then, you want to produce a linear graph that you could use to help you determine spring constant. Let's just do period squared in seconds squared, and then mass in units of kilograms. And then therefore how you could find the slope is you could say that since period squared is equal, or rather, let's start with t is equal to 2 pi root m over k, right? So then therefore period squared is going to equal 4 pi squared mass over spring constant. So that implies that period squared over mass is going to give you the slope right? Or if you actually take 2 different points, right, for both of those, right, that'll actually give you the slope, and that slope then will equal 4 pi squared over k. So therefore, you would get that k is going to equal 4 pi squared over the slope then. And so that would allow you to use a straight line with rise over run slash slope in order to help you find the spring constant. All right, so that would probably be 3 points for part B, 1 for getting the correct axes. There's many different possible things. You could do t in square root of mass if you wanted to. Or, you could flip the vertical and horizontal if you wanted to. That would also be fine. 1 for actually saying that period of oscillation relates to that slope, and then 1 for actually figuring out how that slope relates to k then. All right, different experiment. You have a force probe and a motion sensor. Pull the card to the right so that you get oscillatory motion, and you get force and velocity. Okay. All right, let's see what we got here. Using the data, calculate the change in kinetic energy estimate the change in momentum. Okay, and do your 2 things. Okay, so my guess is probably, let's see, we said 3 points for part B, probably 4 points for part A, I'm going to say now. So that's 7. So I would say probably 2 points for the first 2 parts of C, and then 1 point for the very last part of C then, which would give us probably all 12 points then. All right, so 0.5 in 2 seconds, 0.5 and 2.5 seconds for the second one. So let's go ahead and solve C part 1. Estimate the change in kinetic energy between 0.5 and 2 seconds. Well, change in kinetic energy is just going to be final kinetic energy minus initial kinetic energy. So that's going to equal 1/2 mass, and then Vf squared minus Vi squared. So that's going to equal, let's see, 0.125, 0 minus 0.3 squared. All right, I guess I have to pull out the calculator for this to help us get our change in kinetic energy. So 0.9 times 0.125. All right, so our change in kinetic energy for C part 1 then would be 0.011 we'll just kind of stop there, joules. And it would be negative, actually. Yep, perfect. All right, negative 0.011 joules. All right, have we satisfied the entirety of that question? Let's see before we move on to C part 2. Yep, there we go, steps and substitutions. All right, force time graph, estimate the change in momentum between 0.5 and 2.5 seconds. Oh, that's easy. And how you did that. So for C part 2, the change is 0 kilograms times meters per second because the area under the force time graph gives us impulse, aka change in momentum, and the area from 0.5 to 1.5 seconds is negative and approximately equal to the area between 1.5 and 2.5 seconds. There we go. So there's our 2 points for C part 2 then, right? Let's go ahead and make that a little bit longer so you guys can actually read that. Again, I just took the area from 0.5 to 2.5 seconds. It's approximately 0. That gives you impulse, aka change in momentum. All right, so do the data from the velocity time graph confirm your estimation? Yes, it does. So for C part 3, let's go ahead and write that. Yes, it does, because the change in velocity is 0 meters per second and, between 0.5 and 2.5 seconds. And the mass is constant. Therefore, the change in total momentum is 0 kilograms times meters per second. There we go. All right, so that's it for question 2. Nice. That took about 12 minutes, which is not bad at all. Let's go ahead and take a look at the very last question, which does seem to be a static equilibrium question. So you have all of this stuff right here, and you're actually asked to draw and label the forces acting on the beam. All right, so we do have a few, right? Gravity is going to act at the center, right, of this rod because it's uniform. So therefore, center of mass is at the very center. You are going to have a tension force, which is going to be pointed at that angle theta 1. And then you're also actually going to have a hinge force acting on this as well. And I do actually believe, let me actually go ahead and redraw these. I do actually believe that the hinge is going to exert a force that's also going to be partially upward, because the torques from tension and gravity will have to cancel out. So I think the hinge force is going to look something like this, where you have the two horizontal components cancel out, and now all of the vertical components also end up canceling out. There we go. So that's probably going to be 2 points, I would say, one for drawing all of the forces and one for ensuring that they all cancel out then as well. Actually, let's see. Yeah, probably 2 points. Probably 2 points for that. All right, you now attach it lower to the wall, and what you're asked is you're asked to actually wait, hold on. The other end is attached, the beam remains horizontal. Okay, so if the angle is less than 90 degrees, actually, you know what? Hinge force might actually just be entirely horizontal here. But it is hard to tell because we don't actually know what angle theta 1 is. It doesn't quite look like it's 45 degrees. Yeah, I'm going to actually leave this how I have it here. All right, let's go on to part B. All right, string is attached lower to the wall. What happens to the magnitude of the tension force, and justify using qualitative beyond referencing equations. So I'm actually going to do my justification first. The torque caused by tension must still cancel out the torque caused by gravitational force. The force of tension, or just the tension, must therefore be stronger, since there is less angle between the tension and the radial line. All right, there we go. So tension actually does have to be stronger here. This actually kind of reminds me of one of the physics C questions that I was working on a few days ago. But yes, tension will have to be stronger in this case, in figure 2, because of that. Because since you're lowering the angle between the tension and the radial line, and the torque still has to be equal, the force has to then pick up the slack there. All right. In starting with Newton's second law in rotational form, derive an expression for the magnitude of tension. All right, that's not bad. Net torque has to equal 0, right? So therefore, what we have is you have that the length of the rod. Let's also write that torque is equal to RF sine of phi, right? So what you have is that for the tension, right, what you've got is, torque caused by tension minus the torque caused by gravitational force is equal to 0. And then therefore, right, LFT times sine of theta is going to have to equal, let's see, L over 2 mg then. So therefore, what we're going to have is that Ft is going to equal mg over 2 sine theta. All right, so probably about 2 points for part B, and then another 2 points for part C, indicating that the torques have to cancel out, and then actually solving for tension. So if we got, let's see, that would be a total of 6 points already, which seems a little bit low, actually. So free body diagram, I guess you could give 3 points. One for ensuring that you don't have any extraneous forces as well. So one for getting all of the different forces correct, one for having them all add up to 0, and then one for not, one for also putting the forces actually where they should be. So 3 points for part A, uh, two 3 points for part B, one for getting the correct check, and then two for the correct reasoning that torque is still equal, and then tension has to be stronger because the angle is smaller. So that's 6 points. And then probably 2 points for part C. I can't see it being any more than that. So then that leaves us with 4 points. And I think that each of the two remaining parts is going to be 2 points each then. So is your derived equation consistent? Yes, because sine of theta 2 is less than sine of theta 1. So therefore, f t2 is greater than f of t1. All right, there we go. Easy enough. All right, and then the string is cut and the thing begins to rotate. Sketch the angular speed as a function of time, but before the thing becomes vertical. All right, what's going to happen as a function of time is that the torque caused by gravity is actually going to go down. How is it going to go down? It's going to go down like sine, actually cosine of the angle away from the horizontal then. Angle away from the vertical, actually. Sorry. Nope, horizontal. Sorry. Oh, man. Cosine of angle away from the horizontal, because it's going to be largest when that bar is horizontal, and it's going to be smallest. The torque caused by gravity is going to be smallest when that bar becomes vertical. So I think what's going to happen to angular speed is you're actually just going to actually get part of a sinusoidal function. So it's going to look something along the lines of this then. Because what you're going to have is you're going to have simple harmonic motion if that wall isn't present. This is going to act just like a pendulum, right? And so you're going to get simple harmonic motion. So angular speed should follow a sort of sinusoidal graph right there. So it'll look like that, where the speed starts at 0, increases very quickly because you have a big torque, and then levels off because the torque is getting smaller, and therefore you're having a lower change. All right. And that's it, actually. Wow. So 20 minutes for those two long questions. But thank you guys for watching these videos. I hope that you found them helpful. Next year we get new exam formats for all of our physics exams. I really hope that they don't release 2 AP Physics C sets next year, because that's going to be a lot of those videos are going to be very long, since all of the free response sections now are getting increased to 100 minutes suggested time then. Anyway, hopefully you guys found this helpful, and I hope that you guys have a great summer.